Now, just let me know if you can hear this.
Yes, I think it's working now.
All right, so just rebooted. All right, I'm gonna start afresh. Okay, let's just start all over. And boy, am I sorry for having such a bad day technically. Let me just apologize for all this stuff. The latest issue there was the stream, it wasn't capturing the audio for no particular reason, so I just restarted my computer and that fixed that one. But the first thing I want to talk about was the mid-semester exam. Most of you just did the mid-semester exam a few minutes ago, and we ran into two significant technical issues, which are both I'm really sorry about. The first one was that we maxed out Zoom. I hadn't anticipated that, and the worst part about that was we didn't find out until the 300th person joined. That's when we found out, and of course that was like just moments before the exam started. So at that point, what I did is I stopped the starting of the exam, got another computer with another account because I can't start two Zooms under the same account. Got another computer with another account, and so I was running two Zoom sessions, one from one account and one from another account, and we went on and ran the exam. I posted as soon as I had that working, I posted that in Piazza to tell people that we had the two Zoom sessions going. But I know that Piazza got pretty crazy, and so some of you, there was one or two students who never found out about that. So for you guys, I really apologize. I did try really hard to make sure everyone was aware of that, and I guess the only thing we can do is for the final exam, we'll use Zoom Webinar, which allows us to scale beyond 300. I've never used Webinar before. I've never had to. Anyway, apologize for that. The second issue we had was a really low-level technical issue, and it was actually made me pretty sad because we tested the exam a lot. I spent a large amount of last week, probably about 30 to 40 hours, but perhaps more than that, more like 60 hours working on the exam. And all over the weekend, I had three of our great tutors, including Leo, testing the exam. And we didn't run into this issue. Something happened right before you got the exam, which caused this issue with running the tests. So I can only apologize for that. We tried really hard to make sure everything was perfect for you. And everything was proofread and checked, and the tests were all working and everything. And then this issue crept in at the last moment. So I apologize for that. There's not a lot I can do about it, and we certainly can't reset the exam because it's like I said, it's in the order of 50 hours work just for me, plus all the work the tutors did. So apologies for that. I did try to post instructions on Zoom to explain how to get around that, and I know most students got on fine, although I know it was stressful and inconvenient. So apologies for that. Now, does anyone have any specific questions that I haven't addressed? Leo, do you have any questions there?
No, I think I only got a response saying yes, you're back, and that's everything.
Yeah, all right. So Leo says there's no questions yet. I just want to say that a couple of people wrote me very carefully and sensibly worded comments about the exam, and I appreciate that. If you can put aside your frustration and say what issue you face and so forth, and put that well in a private post on Piazza, that's always appreciated, and I always try to respond immediately on that. I'm not going to respond during the lecture if you write one now, but I'll always try and respond as quickly as I can. And so for those of you who had the grace to do that, I really appreciate it. And finally, before we go on, just remember the exam is redeemable. So if things didn't work out and you feel like you got a bad deal, please understand it's redeemable. And I expect that the mark in the mid-semester exam will probably be lower than in the final exam. So for most people, the redeemable thing is actually a really good deal. Now, Leo, any more questions on the exam? Otherwise, I'll move on to the main part of the lecture.
No, I just got a thank you message from Hoya. Sorry if I mispronounced your name. She said, great effort. We appreciate it.
Yeah, and thank you for saying that, for the person who said thank you. I particularly want to say thanks to your tutors. Your tutors are amazing. And I know sometimes you guys get frustrated by stuff, and we just had to reboot my computer due to some weird bug in OBS or whatever it was. These things happen, and your tutors are just amazing. Leo and Tom and Thomas and Ilya, four of them were working all through the weekend on that exam to help me, and I was working all through the weekend too. So big shout out to your tutors for doing such a great job, and apologies when stuff, despite all best efforts, doesn't come off. We have to learn to live with that sometimes, which is depressing, but
No, now we get questions from Ethan.
Yep.
He asked, why are we testing people's ability to program quickly?
Yeah. Someone asks.
And another question.
Sure.
Oh, sorry. Yeah, please go ahead.
Someone asks about why we testing people's ability to program quickly. Yeah. In this course, we test lots of different things. Yeah. You'll know that in the group assignment, we test your ability to work as a team. Right. In the design exercise, we test your ability to think creatively. In the labs, we test your ability to be consistent and do lots of exercises in a supervised environment. In the final exam, we test as many of these as we can. In the mid-semester exam, we're testing a number of things. We're essentially testing your fluency, okay? And that's by design, okay? That's by design, and it's not about how fast you can code, because the number of lines of code there actually aren't that many. It's about how fast you can think through these problems. And I totally realized that most people won't be able to finish the whole exam. And I said that in the expectations notes on Piazza. And I said that in the revision lecture yesterday. And I said that previously about the mid-semester exam. So yeah, it's done quite deliberately that way for the mid-semester exam. And it's just one of many, many facets. And as you'll notice, if you go and look at all the assessment for this course, this is the only one for which that is the case. That's not the case for the final exam. And it's not the case for any of the assessments. So this is the only assessment where I'm testing your fluency, your ability to move through quick questions, which you've seen the same style of question before, remember, because I've given you these mid-semester sample exams. So can you move through this stuff quickly? And the last question, of course, was one that really required quick problem solving as well as ability to debug things quickly. So yeah, that's my answer to that question. The question was, why am I testing people's ability to code quickly? And that's basically the answer there. Leo, was there anything else?
Another question is the final exam this time pressuring?
No, of course the final exam is not this time pressured. The question was, is the final exam this time pressured? No, of course it isn't. The mid-semester exam is completely different to the final exam. And I did try to make that pretty clear. The final exam is a 3 hour and 15-minute exam. And you can look at the sample exams on the website. You can see how they are. Usually, a lot of students finish their final exam early. And just so you know, there were students who finished this mid-semester exam early. Just so you know, okay. I totally understand most students wouldn't. I totally get that. But yeah, some students did finish this exam early. Someone actually wrote a note to me on Piazza saying, "Is it okay if I leave early?" And they got all the tests passing on the CI. So. Yeah, but the final exam, no, it's a totally different style of exam. You can go and have a look on the course website where I've given you sample exams and I've given you last year's exam, and there's loads of questions for you there to go and practice. And but please do practice, because the style of the exams, as you will have seen from the ones I gave you, the last year's mid-semester exam, you'll see that the exam you set this year is very similar in style. Different questions, obviously, but very similar in style. Anything else, Leo?
No, that's everything.
All right. Well, once again.
Oh, sorry, another one.
Oh, one more.
Can we get some marks if finished part of the task? If just finishing part of the task?
You get marks for every test you pass. That's how it works. It's very simple with the auto grading. You get a mark for every test. So if you did one question and you got 3 out of 5 of the test, you get 3 marks. Okay. And I did mention that in the practice when I went through the revision on Friday. So if you're at the revision lecture, you would have seen that. I showed how it's really important strategically when you're doing these exams to get the easy stuff working quickly and get the marks for those quickly, okay? And the same is going to be true for the final exam, although the final exam is different in this, as I just said a few minutes ago. The final exam is very different, but it will still have the same thing. You're going to have unit tests, and you want to get the ones that are easy to get first, right? It's not all or nothing. So if the question's got 20 marks, there are some questions in the final exam with 20 marks in them. You can get 2 out of 20, which is a lot better than 0 out of 20, or you can get 10 out of 20, or you can get 18, whatever. It depends on how many tests you go through. And I try to structure those tests so that they're not all or nothing. Particularly for the earlier questions, you should have seen that. Anything else, Leo?
That's everything. Yeah.
All right, great. Thank you for those questions, folks. Now it's time to move on. And what we're going to do now is we're turning to collections. You may remember that I said that we're going to do a big coding exercise that uses our notion, what we've learned about collections. This one is, I'm going to spend the whole lecture doing one coding exercise. I think I may finish early, which is great because I'm sure you're all exhausted and want an early mark. I do, but we'll see how we go. But what I'm going to do is I'm going to take these concepts of collections and also the concept of recursion, which we studied before, put them together, and we're going to try in this lecture to write a solver for the game Boggle. Okay, and I'm just going to remind you what Boggle is first. Okay, so here is Boggle. I'll just quickly remind everyone who in case you've forgotten, here's Boggle. It's a very simple game, a word game. I'm going to make this bigger here. Hang on. Whoa, I don't have the side-by-side on. There you go. So here, there we go. Can you see that? You should be able to see this. That's a Boggle game, and it's a dice game. And the idea is you shake these thing around, you get 16 dice. Each one has letters on the different sides, and you have an egg timer. And your goal is to try and find words in the game. So you can see get, G-E-T, is a word there. Set, S-E-T, is a word there. Sent, S-E-N-T, is another word, and so forth. So you've got to try and find as many words as you can. And the rules are that you can't reuse a letter. So you can't visit any letter twice. You can only visit once for a given word. And also the words have to be at least 3 characters long. So you can't have go, that's not valid because it's only 2 letters long. Or no, that's not valid either because it's only 2 letters long. So it's going to be 3 letters or more. They can be connected that way, that is crosswise, or they can be connected on diagonal like that. Okay? So again, S-E-N-T is one word. S-E-T is another word. Get is another word. And what we're going to do, or you can do went even, see W-E-N-T, went. What we're going to do in a few minutes is write a solver for this. We already in a previous lecture wrote the code for rolling these dice, okay? If you remember that, we wrote that code in the previous lecture. What we're going to do now is going to take that code, roll the dice, and then write something that solves it. And you need to think about how we're going to solve that, right? So how would we figure out all the words here? So we're going to look. Can anyone maybe in the chat say something about how we're going to answer this question of how to solve this? How do we solve this? Yeah, can anyone suggest any ideas in the chat about how we'd go about solving this problem? What we're our goal is to find as many words as we can from here. There's an implied premise here that only English words, proper English words, are allowed, and so the way we solve that is by choosing a dictionary. So we'll just use. So in fact, I'm going to use a dictionary that we've already got, just a standard Unix dictionary, and so it's got to be words from that dictionary. That's one thing. The words have to be 3 characters or more. Okay, so given those constraints, how am I going to solve this? Any ideas? All right, let me start by asking you something very specific. If I started at the letter W, how would I find all the words on this particular arrangement of dice that would that start with W, that are legal words?
I got a response from Joshua. So we need to get all different ways to make 3 combinations of letters and match them to the dictionary.
Did they say 3?
Yeah.
Okay, the words can be more than 3, right? We can have 4-letter words, 5-letter words, 6-letter words, everything up to 16. There's 16 dice here, okay? So we've got to find a way to find the combinations. One way to do this in a standard way approach is to visit all the words. So what we can do is we can say, look at WY and see if that's a legitimate word in the dictionary. And we can look at WYR and see if that's a legitimate word. We can look at WYRH and see if that's a legitimate word. And then WYRP and see if that's a legitimate word. And of course, they're not legitimate words. And so forth. And we can keep going like that. And then, eventually we'll come and say WEN and then say N and then T and say, oh yeah, that's a word. Okay? So that's a very time-consuming way to do it, but that would work, right? So we could just exhaustively start at one letter. We start in this corner here, perhaps, and go and look for words. And let's start with R and look RH, RHR, and so forth, and do that. And then try this one and look from there, and then try this one and look from there, and then try this one and look from there, and so forth, and build up a list of all the words that we can find. Does that make sense? Hopefully it makes sense to you all. That's one way to do it. What I'm going to do is I'm going to code this first of all, essentially the way I just said. And then towards the end of the lecture, if we have time, I'm going to show you some tricks that can make this a much more efficient approach. And those of you who are doing 1140, you'll remember we talked about pruning, alpha-beta pruning in the 1140 lecture. And for those of you who are doing 1110 and 6710, the same sort of thing applies. When you do a search, which is what you're going to have to do for your game in 1110 and 6710, is you can do it exhaustively in a really naive way, or you can have some insights that can tell you, actually, you know what, once we've got to WYR, something tells us this is going to be pretty fruitless to keep looking for words that start with WYRH. Can anyone on the chat tell us what insight might allow us to prune things at some point? So I'm looking here and I've established WYR, and then should I keep looking and keep going until I've used up found a 16-letter string, or can I stop my search? Anyway, you can think about that. We'll come to the optimizations later, but I want you to think about that. So if you're finding the coding fairly easy, then try and work out how we can make this search more efficient. And there are a couple of techniques, and we're going to do them in the lecture later in this lecture. But that's the basic problem. And what we're going to do is we're going to start by, where are we here? I've got to find where we did boggle. Where was it? There it is. We're going to start by pinching that code there, pasting it there. And there it is.
I think we are getting some response from chat. People saying we simply can't get any words starting from those four characters.
Someone says we can't get any words that start with those characters. Okay, we can't get any words. How do you know that?
Claire saying there are too many consonants, too many vowels in a row.
Yeah, someone said there's too many consonants in a row. That's a nice intuitive insight, but our program, unless we write an AI, a machine learning thing, we can't use that sort of insight. We have to have a rule. What's the rule? What's the observation? Is there some way we can check that it's actually not some, there could be a Welsh word in the dictionary, some really weird word that originally came from Welsh that has some WYR at the start. Who knows, right? How can we check that? Is there a way we could check that? Basically, the person who said that, they're thinking a good thought, and I want them to think a little bit further about that, okay? Try and think about how you might be able to do something actionable with that idea that you just had. Okay, so what I'm going to do now is I'm going to take this code. I just pinched this code here, and we're going to do a few things. First of all, we're going to do something very simple to make this. We're going to create ourselves two methods here. One is going to be called shake, and the other one is going to be static. What is it going to return? What's the it's going to return an array of char, like that, shake. And what this is going to do is produce a new boggle. So if you remember, let's just hang on before I go any further with this return null. Let's just do this. If we run this program, which is the one we already did back in J11, we run this program. Let's just run this. Okay, run this, and we'll see what happens, right? And this should be familiar to you. All this program here does is, it's still compiling, here it comes. Okay, there you go. So it drew us a boggle, and that looks a bit like that looks like this roughly, okay? So it's a 4x4 grid, right? So there's a 4x4, and that's what we've got to solve. So I can't see anything there. Nab, I guess nab's a real word, N-A-B. We've made it shake the die. That's what we did previously. And what I'm going to do is, instead of it all happening in the main method, I'm just going to extract that out and put it in here and separate out the shaking with the printing, because we're also printing in here as well. So let's just write another method here called static void print. So far what I'm doing is not going to change anything from what we had before, but except to make it, we just call this print boggle.
I just got a very interesting idea from Michael. Is
Yep.
that you could encode all words in a dictionary in a 26 branching factor tree and stop the search if you reach a root node.
Great idea. So, yep. So the message on the chat was, let's take all the words in the dictionary and put them in a big tree where every every node in the tree has a 26-way branching factor. And then that way we can stop the search whenever we hit the end of a branch. That's a great idea. Let's see if we can think, that's a great idea, Michael. Let's see if we can think of a way, particularly the hint here is that we're doing containers, so sets and lists and so forth. Think of a way of basically putting it into action, because you're right on the money there. That's a great idea. And we can do this quite simply using a set, okay? So I'll leave it at that. That's a great thought, and see if we can think further. And we'll come to this later. We'll come back. So keep thinking about that. That's a great idea. Okay, so here we go, boggle, and then what we're going to do here is this is going to do the printing. So here, like this. We need 2 for loops, don't we, to print it out. Let's just do this. We'll take this whole thing, and I'm just going to trim it just to make it easy. So I'm writing a method here, which we don't need the random, but we do need to know the row length. Let's just put that there up the top to make this simpler. Static, final, row. Just put this up here, okay? What's happened here? Why does it not like that? There's the dice, static string. Oh, what's happened here? Something's not right. All right, we'll keep static final int. Oh, that's why I didn't say the type. It's an int. Okay, there we go. Now it's happy. All right, so we don't need this now. We're going to go from here to. Sorry, I just deleted the wrong line there. Okay. 16 dice, and then what we're going to do, we don't need to do the rolling of the dice here. This is just the printing part. Okay. We do not need to do any of this stuff here. All we need to do is print it out. Okay. So we're just going to print out boggle. Okay, and then if you can just copy this in here. All right, so that's a very simple little piece of code. I could have just written that from scratch. It probably would have been faster if I'd just written that from scratch. But what I'm doing is, in fact, I can just say boggle.length. So what I'm doing is going through all the letters in the boggle, and then I'm going to print out that letter. And if I'm at the end of the row, I'm going to print out a new line. Okay, that's all that's doing. Very, very simple. Now this one here, what we're going to do instead is we're going to create a char boggle equals new char array of dice.length. Right, we're going to create this thing. And then what we're going to do here, we already have the row length because we made that constant a few moments ago. We'll just call it row length. Okay, here. In fact, we don't need this. We're not going to print it out anymore because we've got a separate function to print it out. Okay, so now let's have a look here. What we're going to do is we're going to put all these letters into the boggle instead of printing them out. So now we'll just say boggle I equals value. All right. So I could have just said that here, in fact, just to make it more succinct. Let's do that. Boggle I equals that. All right. So just reflecting on what this code does, and we have to return that thing. So the code here shakes the dice. The way it does that is we went through this before. I'm not going to go through it in detail. It goes through all the dice in a random order and then rolls each dice in a random way, and it puts that dice into the boggle and then eventually returns it. So in our main method, we can now rewrite the main method so that the main method goes and so the main method just goes and creates the boggle char like that, boggle equals shake like that, and then we just say print boggle. Okay, and we run this, and it should behave exactly like we had before, where it'll print a random boggle out. Okay, so we've hardly done anything here except refactor the code we wrote last week. Okay, so there's another random boggle. All right, now what we need to do is to write a test, because remember we're going to do test-driven development. So what we're going to do now is write a test. So what we can do is we'll write a thing called test boggle at test. That's how we start all our tests. Okay, and we'll say public void test boggle. And what I need you to do, folks, is to look at that boggle that we had before. If you can remember that there, maybe screenshot it or something. We're going to look at this thing here and think of, maybe you can do it right now while I'm talking. Try and find words in there that should be legal words, and find ones that aren't as well. So we're trying to find tests that will say, for this particular boggle, let's find words that are legal and ones that aren't legal, and then we'll write tests that say, hey, if you had this boggle, then you should have found this word, you should have found this word, and you can't have found this word because it doesn't exist. All right, so we're looking for words. So you can look up on the Wikipedia page if you want to do this while I'm talking. Look up on the Wikipedia page, look at that picture, and you can try and find tests that we should put in here. So what we're going to do is we're going to first of all start off with that array of characters, char, square, dice, and now what we're going to do is just do that exact boggle there, which I believe is this. I could have typed this in before, I suppose, but I did not think of that. H, what have we got? H, R, H, R, E, Y. This should be the same letters that you're seeing if you're looking at the Wikipedia page. Y, P, C, S, W, P, C, S, W, N, S, N, T, N, S, N, T, there it is, and then E, G, O. E, G, O. All right. Let's just check that that's right. I guess it doesn't actually matter if it doesn't match. Oh, there's another word, by the way, ego, E-G-O. It is, that does look right. And then what we can do is something like this. We could say, actually, we can move this here and say static final test dice. There you go. Oops. Test dice, there it is. And then what we can do is we can print that out down here. We can say, we can, instead of doing that, we can just say print boggle test dice. Okay, there it is. We can run this, and we should get the same series of letters as on the screen. There you go. And now, while I'm working, you can keep looking at that down there if you want. Now, let's write ourselves some tests. Okay. What we're going to do is we're going to write a method up here, which was going to be called solve boggle. Okay, so we'll say, and we're going to get it to return a list of strings, a list of strings. So we're going to use the list type, list string solve boggle, and it will take in a boggle, the dice, right? And initially we'll return null. Like that, okay? And then we need to include this one. Remember, we're using container types. So there we go, we're going to include this, import that class. Yep, Java util list, there it is. So we're going to solve this boggle. All right, we've passed on the dice. And then, first of all, we should just do a test to make sure that it actually is not null, because this will fail, because it's, or we could just return an empty list, new list of string. Come on. Oop. That's a mistake. There we go. You don't need that function there. I don't know why IntelliJ wants me to do that. I'll even need to say which kind of list it is. Array list. There it is. Okay, and I'll get rid of all this junk that IntelliJ got a bit excited about and dumped in here. It thought I was... All right, and then we're going to return this. Okay, so what this means is our solve boggle is just going to return an empty list. Okay. There it is. So return an empty list. And then what we can do in test boggle is we can get it to list of strings, list of string, call it solution equals solve boggle, and we'll pass in the test dice. Okay, that's the one that looks like this. Okay, and then we can do a bunch of tests. All right, so we're now ready to run our test. At the moment, our boggle solver does absolutely nothing. It just returns an empty list, okay? So everything should fail, which is how we do test-driven development. Now we're going to write a bunch of tests and say, if we had this set of dice, what should we expect and not expect, okay? So let's do some. Assert true. And so, Leo, if you could read out some for me. Assert true. Result solution dot contains. What can it contain? We can do ego, right? Because that's very obvious at the bottom. So that should be true. And then the message will say did not. All right, so there's a test, and let's just import that. Yep, that's the one we want. Now we'll repeat this lots of times. What other tests can we put in here? Was it nest? Was it n? No, sent. We can do sent. Sent, and we can't do nest. We can do went though. We can do went. Any other words, Leo, or non-words?
We got something here. Cress on set and cress from Joshua.
Was it cress?
Yes, CRESS.
And what was the other word?
CRESS.
Yep.
So cress.
Yeah, I got that one. Was there another word?
Onset. So ONSET.
O-N-S-E-T. Oh, onset, like the onset of a disease. Yeah, very good.
Yeah.
Okay, and then we've got to find some words that are not here. We've got to find tests that we could get wrong, okay? So we've got a bunch of things that... Let's just test this first, folks. Let's just test this. And of course it should fail because we haven't written anything yet, right? So we say run this test, and everything should fail because none of those words are there yet, right? Okay, great. And by the way, we should refactor this. It's convention when you write a constant to make it all caps. Okay, so refactor, rename, and we'll call it test dice. Yes, thank you, IntelliJ. That's just what I wanted. Okay, so the test dice is in all caps. And then we should write some things that are not in there. So assert false. And then we'll say solution dot contains. So the best ones to put in here are things that you might think were words, but actually aren't really words. And hang on, let me run the other thing again so you can all see it one more time. There it is. No, it won't run while I've got that syntax error there, sorry. Here we go, run boggle, there it is. There it is. And now let's find some that we can't do. Like I think I just west, for example, you might think west is a okay word because those letters are there, but it's not actually reachable. Okay, now hang on, I'll include this include this thing here, and then we'll just say west, right? So west is not actually possible. Oh, I need to fix up those messages, don't I? And any other words? Well, I fix up these messages. See if you can tell me any other words that you might think could be in there, but aren't, that shouldn't be. I can think of one straight away that should not be in the solution, that you might think so. Can anyone think of any other examples that should not be in the solution? Well, I'll give you an example. One is go, because go is there, but it's not a legal word because it's only 2 letters long, right? See, it goes down the bottom there. Okay, any more? And all right, let's see if we can have some more. There's some here. One I came up with previously is rhetoric. I think all the letters are there for rhetoric. So let's just put that in there. So that's another word which is there, but another one we can do, another thing you should test for, folks, which is a mistake that your solver might make. The idea when you're writing these tests is you should be trying to guess what mistakes might get made. So another one might be something like nests. Is nest an option there? No, it's not.
Michael just suggests.
Yep.
There's option songs. So SONGS. Yeah, singing a song.
Yep.
Yeah, songs.
And SONG is good, but then you reuse the S. So that's a great example. Okay. So it should get song, but not songs, right? Can everyone see that point? Because to get song is okay, but song is not okay because you have to reuse that letter S twice. That's a good example of what we should include in the test. Okay, I think we've got enough stuff in there, right? So we've now got tests. We've now got a thing that will print things out, but we haven't even started solving boggle. So let's get on with that. What I want to do next is get you to think about this little thing here. Go back to this diagram here and think about how we walk around here. We want to walk around. And I'm going to suggest to you that what would be useful is if I could say for any position, think of this as 0, 1, 2, 3, and so forth. Any position, what are my neighbors? Okay? So if you're at P, this P here, then my neighbors are this one. So P is 0, 1, 2, 3, 4, 5. So if we're on position 5, then my neighbors are position 0, position 1, position 2, position 4, position 6, position 8, 9, and 10. So I've got 8 neighbors. 0, 1, 2, 4, 6, 8, 8, 9, 10. Right? So I've got 8 neighbors. Everyone get that? That's a very important idea. So ideally what I'd be able to do is say, hey, go visit my neighbors. And for any position, I'd have that set of neighbors. Notice that R has only 3 neighbors because it's only got, R is at position 0, it's only got 1, 4, and 5. They're the neighbors of R. But P has 8 neighbors. And E has 5 neighbors, right? And R has 5 neighbors, and so forth. So depending on where these things are located, they have a different number of neighbors. But when we're searching, what you really want to be able to do is say, hey, take me to each of the neighbors and see if I can grow the word. But to do that, it'd be really handy if we had a function that says, give me my neighbor. So what I'm going to do is I'm going to create a list of sets of neighbors. Again, I'm emphasizing that what we're doing right here now is we're doing containers. So you can see here we've got a list of strings, and now I'm going to do something more interesting. It's a list of sets. That is, for every position in our 16 positions, I'm going to have a set of neighbors. I hope everyone can follow that. All right. So let's do this. We're going to say we're going to declare static list of set of integer. All right, and then we'll say new array list. New array list, and it will be of dice.length. Right, so for every, what's happened here? What have I done wrong? Oh, equals. All right, so I've said my neighbors are going to be declared in this list of sets. So for every dice, there'll be a set of where all my neighbors are. So now let's write some code which does this. And what we can do is, like a constructor, you can write a class constructor or a class initializer. And that's what this is. This code here will be executed. Anything I write in here will be executed at the start. That's what static and then curly braces. The code I write in here will get executed when the program starts, when this class is loaded. So first of all, let's declare an array of all the different distances, okay? And so that's like, let's just go back to this. The distances here are, what distance is it to there? It's -1. The distance there is +1. The distance here is -1, 2, 3, 4, 5. It's -5, -4, -3, -1, +1, and so forth. That's the distances to all our neighbors, or our potential neighbors, okay? So let's just declare that first. So it's going to be -5, comma, -4, -3, and then -1 and +1, and then it's going to be symmetric. So it's going to be 3, 4, and 5. So that's all of our potential neighbors. And for one of the ones in the middle, it'll have exactly that distance to all of our neighbors, all right? Then what we're going to do is we're going to go through each one of the 16 positions and create a set which has just the subset of those neighbors that are appropriate for that particular one, okay? So we'll say for int I equals 0, I equals 0, I is less than dice.length, and then we'll increment I, and then what we'll do is we'll say is we're going to find out, we're going to create a new set of integers, right? And this will be the so now we're creating, and notice here I've declared set as the abstract, the abstract type, the interface type set. It's an interface, not abstract. The interface type set, and here this is the concrete one. This is the same pattern we see everywhere. On the left-hand side, we see the interface type. It's very general. And on the right-hand side, we see a specific instance of a list. So this is any list. That's a concrete list. This is any set. That's a concrete set. Okay? And then we've created ourselves a set. We actually don't care how it's implemented, but a hash set's a very common one to use. Okay? So we just want a set. But we have to nominate some concrete one. Here we've nominated a hash set. Okay, then what I'm going to do is go through all the different distances for int d in distance. So I'm going to go through all those distances, and I'm going to make sure that distance is legal for this position on the board. Okay, so the way to do that is you will take the rows and the columns and find out if it's off the edge from where we are. Okay, so for a position 0, then a bunch of them are going to be off the board. If we're in the middle, then most of them, none of them will be off the board. Okay, so we need to find that out. So the way we can do that, there are lots of ways to do that, is we'll find out our position here is I, and that's the distance away from us. So the neighbor's position, neighbor, int n, that's our neighbor, its position is going to be I, that's us, plus d, I plus the distance, that's where they are. And then we've got to make sure that that n is not off the board, right? So how do we do that? Let's find out the row and the column of our neighbor, and then say, and make sure that that is not, we haven't gone off the edge of the board or something like that. So we'll say int n col, that's our neighbor's column, equals n, to find the column number, we do integer remainder by 4, which is row length, right? And the int n row equals the integer division. Okay, so we've got the row and the column of our neighbor, and then what we want to do is make sure that it's only one row or one column away from us, and that n is not off the whole grid. So we can just say the following and say if n is greater than or equal to 0, and n is less than dice.length, then that's okay. And its distance from us is only 1, then we're good, right? The distance of the row and the distance of the column is only 1, so it hasn't gone off, wrapped around. We don't want the case where we're here and our neighbor is over here. That means it's wrapped around. So we're going to check that the column is in just one difference from us. If it's more than one difference from us, then we're in trouble. So we can say math.abs. We'll say our column, which is actually we don't need to know this. We just need to know. We don't need to know the row. All we need to know is the column. I just forgot that. I col equals I. That's what we want to do. All right, so now we've got the column of us and the column of our neighbor, and there can only be one different. If they're more different than one, it means we've wrapped around, okay? And by checking for n here and here, we're checking that it hasn't wrapped off the top and the bottom of the board. Okay, so now we're just going to say if our row and our column, if the difference between them is needs to be equal to 1. Or it can be 0, of course, if it's right above it. Okay, so say I col minus n col has to be less than or equal to 1. All right. So that's, well, we've got to finish the statement. So we say, where's our set die? Dot add d. All right. So we've added d to the set for this die. All right. So if all these things hold, then this distance that we're talking about is a good distance for this particular die. So we add it to its set. Then once we've done all that, we will add this die to the list. Okay, so we'll say, what's the list called? Have we created it? Where's neighbors? I didn't declare it, did I? Oh yeah, we declared it up here. We say neighbors dot add die. Okay, so we've added this set for this die to our list of neighbors. Right, so now we can look up neighbors and find the set of all neighbors for a particular die position. Now let's write a test for this. Test, so let's call it, it's going to be public to be a test, and we'll make it void, public, void, test neighbors. And then what we're going to do,
Hi Steve,
Yeah.
Question from Joshua. I think he's currently asking for line 26. So why it's not add n plus d? Because he said that's not just the distance.
well, that's a good question. The question from the chat was, why don't I say n plus d? Yeah, we could do it either. Okay. If I have d, it tells me the distance. Oh, actually, let's just add d. You could do it either way. That's fine. It's all good. There are multiple ways to do this, right? If this was a list of distances, so we'll make a list of set of neighbors. If we do that, then we make it n for the neighbor. But we could have made it a list of set of distances, in which case it would be d. Either is fine, but we have to make sure we know which one it is and don't get confused, because if it's distances, then we have to add it on. If it's neighbors, we just take the number. So we'll just use n as a neighbor, okay, instead of using d. That's a great question. Hopefully my answer made sense. If it didn't, please say so in the chat and I'll explain further. So now what we're going to do is test, do some tests on our neighbors. And I've got a few suggestions. If anyone can get any examples of good tests we can do to see if our neighbor list is wrong. In I equals 0, I is less than dice.length, I plus plus. So we'll go test all these sets, right? And then for each set, what we want to do is we want to say things that can't be true. Okay, we shouldn't be in the set ourselves. So we say set, we can say assert false, neighbors dot get I, that is get our set, and it shouldn't contain us, right? So we should not be in our set of neighbors because we're not our neighbor, right? So then we'll just say okay, so that's a mistake. The other thing we can do is just see if something silly like a negative number is in there. These are only a few tiny, very simple tests. So you should never have -1 in the set of neighbors. You should never have 16 in the set of neighbors, right? And then we can do some assert trues, ones that we know are true, right? So we can say assert true, true. We can say neighbors dot get. Let's go to position 0. That's where that R is down there, and check that it contains. It should contain 1, right? And then say right. So it should have position 0 should have had 1 in it. And the other more interesting one would be, what is it? 1, 2, 3, 5. Right. Position 5. It should also contain 5, right? Whoops, hang on. I accidentally pasted something weird here. There we go. Okay, so we're going to make sure it contains 5 as well. All right. Now let's run our test. Now, test here should be testing that. We should have written this test before we wrote that code, by the way. I just did this out of order. Bad me. All right, let's run this test here. And it should pass, right? Because we've gone and we think we've implemented the set of neighbors correctly. Running the test, and it failed. Why? Included 16 in the neighbors. Ha! Where did we do that? How did we do that? Let's have a look, folks. Can everyone see this? Look at this. It says included 16 in the neighbors. We expected it not to be in there, but it's in there. So our test actually helped us here. How did we do that? Let's have a look. Where have we gone wrong? So if I is less than dice length, that's funny. I is less than dice length. How can we be including?
Hey Steve, Ethan and Michael just pointed out it's looking for 15, not 16 in the test.
Oh, all right. You have to write your test correctly, folks. So I wrote 16 in the text here, but I wrote 15 there. That's very confusing. All right, let's run this again. Well done, folks. This is team programming at its best. Okay, we have passed. Hooray, we now have a method that finds our neighbors. Now let's move to the more interesting part of the problem and actually try and write something that will, well, actually we're still not quite ready to do the interesting part. Let's write something that reads in the words, okay? So we have to write something that gets our set of words. And what we're going to do is we're going to take a set of words and update that set. So we'll say static void read words, and then we'll take a file name, and then we'll take and a set of words which we're going to update. This set will be empty initially. And what else do we want? That'll do to start with. Okay, so we'll start off with that, and then we're going to read something in. So equals new. What is it? New scanner. And we're going to pass it a file. Okay, so we say new file. Whoops. And then file name. Okay, and now it will ask us if we want to include that one. Yeah, we do. And then we want to include that one. Yep, we do. And now it asks whether we want to surround it with a try catch, and we absolutely do. This is something you need to do when you access a file. You need to have a try and catch. And this is an exception handler. And later on in the semester, I'll explain this in more detail. But Java wants to make sure that if something goes wrong when we're reading from that file, that we'll catch the exception. Okay, so that's what's going on there. So now we've opened this. We're going to open this file. And we're going to count how many words we've got. 2. So let's just add that. Int word count equals 0. So we'll have 0 words to start with, and we'll start adding our words in. And then what we're going to do is we're going to read stuff in here. One thing you'll notice is if you look at the dictionary, what I've got is I've actually got the words in here. Have a look. Have a quick look at this, folks. There it is. There's our words, right? It's just a standard dictionary from a computer, from a Unix dictionary. So it's just a whole bunch of words. It actually doesn't matter as long as we agree. Whoever's playing the game agrees these are legal words. Then we can use it. Okay. So what we're going to do is we want to convert them all to uppercase so we don't have confusion. Because notice these letters here, they're all uppercase, and that's the way it's done in the game. So let's just convert all the words to uppercase. Okay, which we can do easily enough. So say while s.hasNext. Then what we're going to do is take that string, so we can call that word, string word equals s.next, and then we're going to convert it to uppercase. So s.next to uppercase, right? So that's going to convert everything. We don't need that to uppercase. It's just going to convert it to uppercase. All right, so now we've got an uppercase word, and we're going to increment the word count, and we will and put our semicolon there. And then what we're going to do is add it to our set of words. Words.add word. Okay, so what have we done? I think that's about it. So now we're just going to write something here which will print this out. So we'll say s out. We'll say read in word count words okay, so we'll say what the size of the words was, the set of words. Okay, so now what we can do down here is we can call that somewhere down here. We'll do it at the beginning. We can say we need to declare this list of words. Let's make the static up here. So that's our neighbors. Let's have another one up here called static. Well, actually, we can declare it down here. We don't need to make it static. We'll just declare it down here. We'll say string. Oh, sorry, it's a set, right? Set of strings, words equals new hash set. Remember, we've got to say what concrete type of set it is. And then we'll say read words. And the file name, and it's going to be something like assets/dictionary.txt. And pass the set in. Words. Okay. All right. Now let's run this, and it should have read in all our words, and we should find out how many words there were. Run boggle.main. Okay, so it read in 80,000 words, and it created a set with 80,000 words, which tells us, what does that tell us? It tells us there's no duplicates in our dictionary. That's great. Okay, and who was it? Was it Michael or someone else had an idea for optimizing later? You might want to think about how we could optimize when we actually read the words in. There's something we can do there. But we are now at a position where we can solve boggle. So let's try and write this, okay? So actually we can put this up here. We'll write it up here. There's print boggle, test boggle, solve boggle. There's our solve boggle. There it is. Okay, so let's read it in here, and we will take this up here. I'm just moving this around. Okay, and we can put solve boggle at the top here, down here in our main method. We can say boggle.shake, and then we can say solve boggle. Oh, what have I done wrong? Oh, I didn't say static. Static solve boggle. Okay, solve boggle. And then we'll just pass it the boggle. And again, it won't do anything because at the moment we're just returning an empty string. So we've finally done a whole bunch of setting up and we're ready to actually try and solve our boggle. Where are we? Printing boggle and shaking and oh my goodness, I just there it is there. Okay, so that now is the thing for solving the boggle, and we've got our set of words. We've read those words in, and what we want to do is imagine we had a thing which would find the words given the starting point in the boggle. So let's now just go through that list. Imagine we've already got that. Well, in fact, we can write the template for that in a minute. We'll call it static. We'll just do that in a minute. Then what we're going to do is go through every position. Go through each position and say, find the words that start here, find the words that start here, find the words that start here, and so forth. And each time we'll add them to our set. Okay? So let's go back to here. So we'll say for int I equals 0, I is less than 16, 16, typo again, so I just hit the wrong key. That's probably what happened before. We'll do this, and we're going to go and find the words for that position. Okay, so we'll say find words, and we'll pass it the boggle that we have. Where is the boggle? That's dice, called dice, right? It got passed to us as dice, and then we will find use the number of words here. Pass the empty word set in, and it'll add to that set. And there's the dice. What else do we want to do? And then we'll say it's the dice, and then the position, of course. And the position is I. Now, that's not complete, of course. There are a few things we need to think through here. When we go and do this stuff, what we need to do is we need to make sure we only use each word once, right? So let's go here. Each letter can only be used once. So what we really want is a Boolean array to tell us whether that has been used or not, okay? And so when we've used it, we need to take it out and say, okay, we can't go back there because it's used. And once we're finished using it, we'll put it back in, okay? So let's create ourselves a list of used things. So we'll say Boolean used equals new Boolean, and then we'll have 16, so it's dice.length, right? So we've got a Boolean for each one of these, and we'll pass in here the ones that are used, which is, the list of used things, which of course starts off with everything not being used. All right, the other thing we really want to do is we want to think of it in terms of growing. So we're going to write this thing recursively. So really what we want to do is say, okay, let's imagine we're starting here. So this is a bit easier to do because we all know that there's actually some words here. Let's start here. We're going to start here and say, find the words from here. And to solve the problem recursively, we can say, you know what, if we find the word from here, it's going to be a word that starts with G that has whatever we can find from here. So we'll say start with G, that's our prefix, and we call it G because that's what we're on. And then go here and say, okay, add this on and find the words that go here, but start with G. So our prefix is G. So then you can end up getting GET because your prefix keeps growing as you move to the next dice. So let's do that, and we'll have a prefix here, and the prefix will be nothing. When we enter in, it'll be nothing. Okay, and you will keep adding into that prefix. And I think that's pretty much all I want to do. The other thing we want to do is create a set for the actual found words. Right, so we want to say set of string boggle words, that's our solution. Right, so we now created that as well. I'm going to pass that in there, and this thing should grow those things. Okay, so that set should grow. The other word set is the ones that got read in from the dictionary. That's the ones that get used. That's the dice that we're the list of dice that we're playing with, right? These ones, and I is where we're at the moment, and that's the prefix. Okay, then all we need to do is we need to return. This is a set. We need to return it as a list, and the way we do that is we need to convert that into a list. And the way we can do that is like this. We can say array list. And we can just do this. You can create an array list out of boggle words. Why can't we do that? Expression, return, new, I guess. You gotta say new, yeah. Okay, make a new one. Okay, so there we are. That should be okay. Yeah, it's okay now. All right, so what we've got here to solve boggle, what we're going to do, first of all, we're going to read the words in. Oh, I said RTN. Here it is. I already wrote that. I already wrote it there. All right. So what we're going to do here is we're going to read all the words in, create an empty set of boggle words, they're the ones we've found, and we're going to create a list of all the places we've visited, which is initially going to be false for all of them. And then we're going to go through each dice and start looking from that dice. Start with words that start at that position. Okay, and there's 16 of them. And they're going to accumulate all their words in the boggle words set. And as that set grows, they'll add them in, and eventually we'll return that set. So now what we need to do is to write the kind of interesting one, which is the find words method, which is a recursive one. Okay, so let's write that, and that's here. And we need to add in some arguments. So the first one is going to be the first one is a boggle word. So that's a set of strings, set of string boggle words. They're the words we found. And then we're going to have another set of string, which is the actual words in the dictionary. Like that. And then the set of things we've done. So it's a Boolean array. Used, that's the used up ones. The actual boggle that we've got, so that's a char array called boggle. And then we've got our position, which we can just call that the starting place. And then finally what have we got there? The prefix, which starts off as nothing. Okay. Right, now this is our recursive method. So for every position we're going to go and do the find words. So the first thing we want to do is to say that now the place we're at is used. Used of this position equals true. We don't want to come back here. And when we finish this method, before we return, we want to make it false. Okay? What that means is when we go and do our path, we won't come back to this place because we'll notice that we've already been here. We won't visit places that we've already been to. Okay? So we'll write all our code in here. And then what we're going to do is we're going to visit all of our neighbors. Okay? So our candidate is going to be, we don't know if it's going to be a real word, is going to be candidate equals the prefix plus the letter we're on, which is empty string at the start, plus boggle start. Okay? So we take that prefix, we add in this, and that's our candidate. Now, if our candidate's actually a word, if candidate is greater than or equal to 3, and words contains a candidate, boggle, no, what did I call it? Dictionary. I said dictionary, I called it words earlier. Let's do that. It contains the word, the candidate. Then we found a real word. Okay? Candidate or length, right? So if the length of this word is greater than or equal to 3 and it's a word in the dictionary, then we found a word. Okay? So in that case, we can add it to the boggle words. Terrific. All right? Whether or not we found a word, we need to keep searching as long as we haven't exhausted the possibilities. So what we're going to do now is we're going to say, for each neighbor, let's do the same thing again, as long as we haven't already visited there. So we say, for int n in our set of neighbors. Okay, so what I did there is I go to the neighbors list, get us, our start position, pull us out, and then go through all the neighbors in this set. Okay? And then if we haven't already been there, if used n, if it's not used, that is, we haven't visited there, then we recurse. We'll say find words and pass in the boggle words, the dictionary, the list of things that are used, the boggle, the starting position, which is now n, because we're now moving to a new position, and the prefix, which is now the candidate. Okay, and then maybe we're done. Let's give it a go. Let's see if this works. Oh, I didn't actually write anything at the end to, it's working, it's doing something, it's chewing away on it, but I didn't, okay, it finished. Terrific. It did something, but we don't know what. So what we want to do now is we want to make that main method actually print something out, okay? So let's just do that. We'll go through the list, okay? So let's just do that. All right, so we printed the wrong one out anyway. We want to print this one out. We might as well print it before we solve it. That'd be kind of nicer. We can stare at what we're getting before it prints it out. And then we'll solve it. And then what we're going to do is we're going to say, hang on, solve boggle. What's that going to do? Yeah, we need to capture the return value. Okay, so we didn't actually grab that. Okay, like that. Okay, so that will return a list of all the words we found. And then what we can do is we can say sout found solution.size words. And then we can print them all out. We can do something like this. We can do collections.sort solution like that, and then we can just go through the whole list and print them all out. So we can just say for string w in solution sout. Okay, so let's give this a go now. So now we've still got this. So now if we've actually found something, it should print out how many we found, and it should print out that solution. It found 0 words. That's not so good, okay? So it didn't find anything, okay? All right, so let's find out why it didn't find anything. All right, let's go up here. Solve boggle. Find words, boggle words. Okay, we're going to go and add in for each one of these, and presumably that's not finding anything. So let's go here and see what is going on. If it's greater than 3 and it contains a candidate, then we found one. Okay, and we add in that to the candidate. Okay, and then we go to all of our neighbors. If it's not used, then we recurse and we find the words, taking the set of boggle words, which is initially empty, and what's used, the boggle, and the prefix. What's the prefix? Oh, there's the problem. The prefix needs to be the candidate now, right? The prefix keeps changing, right? So the candidate. Okay, so we get given a prefix, but we grow that prefix with the letter that we're on. Okay, so each time we recurs, our prefix gets bigger and bigger. And I didn't do that. So now let's run and see if that was the only problem. That was definitely a problem. Let's have a look here. All right, it did something. It reckons it found a bunch of words. Found 124 words. So let's have a look here at what it did. It found ale. Can you see ale in there? ALE. That looks good. ALS. I don't know if that's a word, but there you go. Also ALSO. All right, this is looking promising. Okay, it looks like we've got a solution. Now we should test our solution. So how do we do that? We should run test boggle. Let's run our test. Run test boggle. So it's running it using that boggle that we gave it, the test dice. And let's see if it passed our test. All right, so it found ego, sent, went, press, cress, onset, song, and did not find west, go, song, and rhetoric. looking good. So what this is telling us, folks, is that we've actually got ourselves a solution to boggle, but it's not necessarily a very fast one. So let's just do a few more things to make this a little bit nicer. So what I'm going to do here is sort this in a slightly nicer way. So we can use a lambda here and sort by the word size, because that's actually important in boggle. String S1, comma string S2. And what we'll do is we will sort first of all on their length. And if their length is the same, then we'll just do a string comparison. Okay, so we'll say if S1 dot length equals S2 dot length, then we'll just say S1 dot compare to S2. So that's just a string order. Else return oh, you have to say return here. Return. So if they're equal in length, then we'll just use the string comparison, the string, however it compares strings, which will be lexicographic. Otherwise, we'll do the length difference, because in boggle we care most about length, right? So we'll say S1 dot length minus S2 dot length, and we'll return that. So I should have said return. Okay, and then we put a semicolon in here, and we can indent all this stuff so it's actually readable. Okay, so that's our lambda expression. Sorry, ugly formatting here. So now that should now sort our thing according to the length and then lexicographic. Let's just run this. And let's actually use the test dice rather than the shake. So we'll just do that. Why would we do that? It just helps us when we're testing to see if to use a reliable one that we know exactly what it's supposed to do when we run this. Oops, hang on, I just ran the test again. I didn't mean to do that. Okay, that shouldn't have changed the test at all because it didn't actually do anything of substance. Now I'm ready for tips on how we should make this faster. Okay, we've got the thing working. I'm ready to start talking about how to make it faster, and I've got some ideas. And we're just waiting for the solution here. It's not the wrong way around to what I wanted. I should have done S2 minus S1. So we want the longest word first. And we'll do it one more time. And now it should have the longest word first. And the longest word I found there was a word called cresset, which I didn't even know was an English word, but there you go. C-R-E-S-S-E-T, cresset. Okay, we have a solution. I'm now looking for tips on how to make this simpler. And one way we can do that, let me just tell you one way we can do this. If we have fewer words to look up, hang on, oh, wait. One more thing we can do here is actually say how long this whole thing takes. That way we can actually concretely find out if it's faster or not. Okay, so let's do this. We'll say a long start equals system dot current time in milliseconds. Then we'll say end equals system dot current time in millis. That's the start and the end. And then we can add to this in end okay, so that'll tell us now how many milliseconds it takes, and let's just see what it said. And then we can see how much we improve things by as we add these optimizations in. Okay, let's see what it said. Okay, it took 7,000 milliseconds. In other words, it took 7 seconds. Okay, about 7 seconds. Now, one thing we can do is to prune our dictionary. Okay, we read all those words in. Where is it? We read all these words in. But if the word that we read in from the dictionary isn't a word that can possibly work, it can't possibly work because it's got letters in it that aren't in our set. If that's the case, then let's get rid of it, because there's no point of including words in our set of words to search through if they're words that can't possibly make a boggle word. And likewise, we can get rid of ones that words that are not that are too short, for example. Okay, so let's write ourselves a little method here called boggleable. Okay, so static boolean boggleable and probably got an A in there, I guess. Boggleable, and what we're going to take is in a word, and then the actual boggle that we've got here. So that's a char array, boggle. Okay. So now the first thing we know is if the word length is less than 3, throw it away, right? So if word.length is less than 3, then we don't want it. Or if the word is greater than 16, it can't possibly work either, right? So we can just get rid of all those words from the dictionary. So those words are no use to us, okay? Then what else we want to do? We want to find out the list of letters that are usable. We're not going to do a search here and find out if it actually works. All we're going to do here is say, is this even possible? Is this even plausible? For example, if we don't have what letters don't we have here? Okay, so we don't have Z in here. There's no Z in this set. If we don't have Z, then there's no point in reading in all those letters that start with Z, okay? And in fact, there's 26 letters in the alphabet. We've only got 16 on the thing here. So there's 10, there's a large fraction of the whole dictionary that we can just exclude straight away. So let's just exclude those. We don't have to do any fancy searching. We just need to say, okay, this doesn't exist. So we say character, we'll make a list of characters, usable, equals new array list. And then what we're going to do is add in all the letters in our boggle. So we'll say for char C in boggle, and then we'll just go and add them. Okay, so now we've got a list of all the ones that are usable. Okay, and then we're going to go through the word that we just got in and find out if any of the letters in there are not ones we want. There are multiple ways we can do that, but one really simple way to do it, one very explicit way to do it, if you like. And then, hang on. Int I equals 0, I is less than word.length, and then increment through there, and oops, and then the letter that we want is the equals the word.char at whichever index we're at. Okay, then what we're going to do is we're going to say if the set contains the one we want, if usable contains L, then we're good to go, but let's remove it, okay? Because then, okay, so because we can't use it twice. So notice this is a list, not a set. If this were a set, it wouldn't allow duplicates because we could have the letter A in there twice. And what this will do is we'll say if we found an A, take it out, and there could still be an A left, all good. Then there's only going to be one A left after we've taken that out. That's why we're going to remove it, and that's why we're using a set. If it had a list, if I'd used a set, then removing A from the set would mean we can't have any A's in there, which would be incorrect, okay? Else, if it's not in that set, then we return false because we're done, right? And then finally, if we got through all that stuff, we can return true. So now, when we read the words in, let's just check if the word is boggleable. So we'll say if let's actually make another counter, int okay, so then what we're going to do is going to say if boggleable word, now we have to add in the boggle here. And then would say two things. We'll increment our count of usable words, and we'll add that in there. Okay, so we've incremented the number of usable words. Then we'll say, make it set. Okay, and then we need to pass in that. Where does this happen here? Where does this get called? We've got to add it in here. Okay, so now we're passing the boggle up to the read words, and it's going to go and find these words. Now let's see what happens. Remember here it took 7 seconds and it had a set size of 80,000. Let's run it now and see if we've reduced the problem. And then I'm going to ask for any other optimizations from online. Oops, that just failed. What have I done wrong? Exception, 67 is out of bounds for 16. Boggleable. Remove L. If it contains L, then remove it. What? Oh, I know what's wrong. Okay, we've got to remove. Remove takes the argument of the index, not the actual value. So, because it's a list. Okay, so what we need to do now is say which. It's not a set. Remember, it's a list. So we're now to say remove usable dot index of L. All right, so that's going to say find out where in the usable array L is, and then take that one out. Okay, you can't just sort of say remove L, because it's going to treat L then as a number, and it's number 65. You see here's number 67. It's going to take that as a number and try and remove 67. Well, there's only 16 things in the array, so that's not going to work. All right, so let's go this again. Remember we had 80,000 words and we had 7 seconds. Let's see if it's any better now. Okay, look. Wow, it's reduced the set down to. It's reduced the set massively. The set size is now only about 2,000. It used to be about 80,000. Okay, so it moved it from about 80 down to about 2,000. We still got the same words, right? We still got the same set of words there. So it did solve the problem just as well. And we've reduced the time from 7 seconds to 5 seconds. Okay, the next question is, can we optimize this further? And the answer is yes, we should be able to optimize it further. And the question is, how can we do that? And I'm looking to people online to give me some suggestions. All right. Any suggestions from online?
Not yet.
Okay, someone had a suggestion about the tree. Who was that?
It's Michael.
Michael had a good suggestion about the tree. So what I'm going to take his suggestion up, but I'm going to do it in terms of sets here. And what I'm going to suggest is that, let's just go back to here. I gave this weird example. If we did something like this, we could know that if there are no words that start with WYR, let's not go any further. So what we can do is we can create a set of all the beginnings of all of the words. So not just the words, but the words and their beginnings. So it's going to be a set of prefixes. Now, when we're searching, if we get to something which is not in the set of prefixes, then we know it can't possibly be leading us to a proper word because it's not the beginning of a legitimate word. So when we read in, we're not just going to have a set of words that come out, but a set of prefixes. So that's very close to what Michael had suggested. We're just going to do it slightly differently, okay? So the way to do that is to add in another set here. Set of string prefixes. Okay, and we're going to add in a prefix. And all we're going to do is when we go and add this in here, we're going to count how many prefixes. While I type this up, folks online, I want you to try and guess for some set of words, like here we've got 2,000, 1,900, how many prefixes will there be? Is it going to be 10 times as many prefixes, roughly? Is it going to be the same number of prefixes as words, or what? I want you to try and write that down, try and think about that and make guesses. So I'm going to start off by saying prefix is equal to 0. I'll just use that because it was clashing with this name up here. Okay. And then what we're going to do is we're going to say, actually, I don't need to do that. I can just say prefix.size later on. Okay, so then what I'm going to do is I'm going to say for int I equals 0, I is less than word.length, word.length, I plus plus, and then I'm just going to add to our prefixes list. Oops, my goodness, that's not what I wanted to do. Add word.substring 0, I. Right, so that's going to add in the prefixes. So now we're accumulating ourselves a list of all of the prefixes. Okay, making a word set of size that plus and a set of and okay, there it is. So we've read in this many words, and now what we're going to do is we go and find these words here. We'll create a set of prefixes here. Set prefixes. And then when we go to solve it, we'll do the same thing. Solve boggle. Okay. When we do the find words, we'll say words, and we'll say prefixes as well. Prefixes. Okay. And then here was the words. We're going to have another set in here, which is the prefixes. And then we've got to recurse here, do the same thing, prefixes. There it is. Now what we want to do is we know that here it says word contains the candidate. That's great. But if the we get to here and the prefixes does not contain it, then we're done, right? There's no point in looking any further if the prefix isn't in there, right? So we can just say if okay, so we're only going to do this, continue the search if that is in our set of prefixes. Now let's give this a go. I think that might be enough to make it go. Let's try. So it took 5.5 seconds that time. Whoa, it looked faster, right? Let's see what happened here. Same number of words. It went from 5.5 to less than 1 second. And notice that the number of prefixes is actually remarkably close to the number of words. Okay? This is really interesting. So what we have, folks, I think with that we can declare victory. And it's a little bit early, which is fantastic. But let's just hang on. Let's just do one more thing before. Oh, we're actually still got the bio. I don't know if I actually even added the slides for the biography. All right, 1 second. What I wanted to do here was our main method. Okay, let's make it a random one again and try it for some randomized ones here. Okay, and what have we got here? We pruned it down to 600 prefixes. We found 58 words in 1 second again. And we'll run this again. Now, folks, I'll run this a few times while you're waiting. It's really fast that time. A lot of words too. Wow, this is a big one. We found 292 in 1 second. Okay, that's a great one. Folks, let's recap on what we did here. I try to show you a number of things. First of all, we use containers. We use lists. We use sets. Okay, we use sets when we didn't care about the order. We didn't care about duplicates. We used lists in places where we did care about duplicates. We also used a list of sets. That's how we did our neighbors. Remember, for every die, we had a set of neighbors. So we had a list of dies, and for each die, we had our neighbors. We built a solution by doing a search, And then we made our solution significantly faster by doing two things. One was, let's ignore words that can't possibly be answers. So we reduced a set of our dictionary, and we reduced it by a factor of 8. We went from about, I think it was a factor of 8. So, no, it's a factor of 4. Okay, we went from 80,000 down to 2,000. So it's a factor of 40. Sorry, a factor of 40. Right, so we reduced by a factor of 40. That's a big reduction in the size of the dictionary. And then furthermore, we had the insight that I think came from online, that there's no point in keep looking if we've got a prefix which isn't the prefix to a real word. So if we're partway in looking, you don't need to keep looking if we already know there are no words that start this way. Now you can implement this multiple ways. Someone on the chat, I think it was Michael, said, okay, let's have a tree and walk that tree. And the way I did it here was to create a set of all the prefixes. And if we found that where we're up to wasn't in the set of prefixes, then we knew straight away there was no point in looking any further. Okay, and another thing I want to point out to you, which is really important, we used tests. And we tested it when we had a really simple solution. It is a very important technique to use. And I drum this into all my PhD students, and we do this in our most advanced software development. And you have to do it this way. You build a simple, naive solution first, then you test it, and you make sure it's working correctly. And then when you're trying to make it smarter, you always have a working solution and incrementally make it smarter and smarter, rather than to try and design the cleverest solution you can possibly imagine and implement that all in one hit. So that was the other thing that we did. Now, I don't know if I've got a biography here, do I? No, I do not. So we're going to miss the biography today. And with that, I'm going to finish up, and I wish you a good week. Don't forget, on Friday, we've got a guest lecture. I want to plug this lecture because I think a lot of you might find this interesting. It's Penny Kybers, one of the academics in the department, and she's had a really interesting career. And a large part of her career has been in the games industries, which some of you may find interesting. Okay, so she's our guest lecturer on Friday, and so please come along for that. That guest lecture is for everyone. The previous guest lecture was just for 1140 because it was on the 1140 game. This one is for everyone, and you're really strongly encouraged to come along, and you get to ask Penny. There'll be opportunity for you to ask Penny questions about the games industry and games development and anything about life as a computer scientist. So please come along, and